This simple metal jaw saved more lives than any medical invention of the 1800s. It's called a safety brake, and without it, skyscrapers couldn't exist. An ex-factory worker named Elisha Otis figured it out in 1852 in a rented workshop in Yonkers, New York. He had almost no money, no formal engineering training, and no investors. Before 1852, elevators were death traps. The problem was simple but deadly. How do you stop a multi-ton platform in the fraction of a second after the rope breaks? But how do you convince the world your invention works when the only proof is cutting the rope beneath your own feet? Let's start with the engineering nightmare. By the 1850s, factories and warehouses were using freight elevators to lift heavy loads. These were simple devices: a platform, a rope, and a steam-powered winch. The problem? That rope was the only thing between you and gravity. Hemp ropes frayed, metal cables kinked and snapped, and when they failed, the platform fell at 32 feet per second squared, the acceleration of gravity. Workers died regularly. Insurance companies refused to cover elevator accidents, and building owners had a limit. You couldn't build higher than people were willing to climb. You know why? The stairs. Climbing 6 flights of stairs multiple times a day was exhausting, and moving freight up those stairs was economically impossible. So here's the engineering challenge. You need a mechanism that does nothing 99.99% of the time, but activates instantly when needed with zero human input, catching a multi-ton falling platform before it accelerates to lethal speed. You have less than half a second, and the system has to work every single time. Engineers tried everything. The first approach was counterweight systems. The idea: hang heavy weights on the opposite end of the cable. If the platform cable snaps, the counterweight drops, pulling a brake lever. The problem? Now you have 2 cables that can fail. And if the counterweight cable snapped first, you just made your elevator heavier and more dangerous. Next attempt: spring-loaded clamps that would squeeze the guide rails when activated. You'd pull a lever, springs would compress, friction pads would grab the rails. The fatal flaw? It required human activation. By the time someone realized the cable snapped and pulled the lever, they were already falling at lethal speed. Human reaction time is 0.25 seconds, not nearly fast enough. Some tried tripwire systems. If the platform dropped too fast, a wire would trigger mechanical dogs to bite into the rails. But these were either too sensitive, triggering on normal operation, or too slow, requiring several feet of fall before activating. Here's what every approach had in common. They all required the failure to happen first, then activate a separate mechanism second. That gap between failure and response was killing people. Elisha Otis was working in a bedframe factory in Yonkers, New York. They needed a safe freight elevator to move heavy machinery between floors, and Otis, who had been a mechanic, a wagon maker, and a doll maker, was asked to solve it. He was looking at a broken wagon spring one afternoon when he had the insight. What if the brake didn't activate when the cable failed? What if the brake was always trying to engage and the cable's tension was the only thing holding it back? Reverse the logic. Don't make the failure trigger the safety, make the safety the default state, and the cable's tension override it. It's brilliant when you see it. The cable breaking isn't a problem to detect, it's the solution to the problem of activation. Okay, let's walk through how this works. Imagine you're standing on an elevator platform in 1853. Above you, attached to the platform's frame, is Otis's mechanism. 2 metal jaws, basically iron catches with sawtooth edges, sit on either side of the wooden guide rails that run up the elevator shaft. These jaws are spring-loaded. Specifically, they're mounted on a powerful leaf spring, the same kind used in wagon suspensions. That spring wants to push the jaws outwards into the guide rails. But here's the key. As long as the elevator cable has tension, it pulls on a linkage that compresses the spring, holding the jaws away from the rails. The cable isn't just lifting you, it's actively restraining the brake. The moment that cable tension drops, whether it snaps, frays, or even just slackens, the linkage releases. The spring expands, and those jaws slam into the rails. Now here's where the physics gets beautiful. Those sawtooth edges aren't random. They're cut at a specific angle, about 60 degrees. When the jaw bites into the rail, the downward force of the falling platform actually increases the normal force between the teeth and the wood. The more weight you're carrying, the harder the brake grips. It's a self-tightening mechanism. The load is fighting against itself. And because the brake engages across the entire length of the jaws, typically 18 to 24 inches, the deceleration is gradual enough not to injure passengers, but fast enough to stop a fall within 2 to 3 feet. Let me put that in perspective. Without this mechanism, a 4-story fall gives you about 2 seconds before impact. With it, you drop less than 3 feet before stopping completely. Elisha Otis wasn't a trained engineer. He was 42 years old, had failed at multiple businesses, and was working as a mechanic for hire when he invented this. He built the first working prototype for his employer's factory. It worked, but nobody cared. Elevator manufacturers said it was unnecessary. Building owners said existing elevators were safe enough. Insurance companies wouldn't even evaluate it. Otis realized people wouldn't believe it was safe until they saw it fail to fail.
So why did this matter? Because in the 1840s, elevators were death traps. In New York alone, dozens of workers died every year in elevator accidents. Freight elevators in factories, mines, construction sites, every industry using them was hemorrhaging human life. And that limited everything. Buildings couldn't go higher than 5 or 6 stories, not because we couldn't build them, but because nobody would work in them or rent space above the 4th floor. You know why? The stairs. Climbing 6 flights of stairs multiple times a day was exhausting, and moving freight up those stairs was economically impossible. But the real problem was psychological. Even when early passenger elevators existed, people were terrified. Wealthy people, the ones who could afford to rent upper floors, simply wouldn't risk it. The rope, that single visible point of failure, terrified them. So when Elisha Otis stood on that platform in 1854 at the Crystal Palace exhibition in New York and cut his own cable with an axe, he wasn't just demonstrating a mechanism, he was breaking a psychological barrier. The platform dropped 3 feet, the jaws caught, and Otis calmly said, "All safe, gentlemen." That single demonstration changed everything. Look around you right now. If you're in a city, you're probably within sight of a building that wouldn't exist without what we just discussed. The Otis safety brake didn't just make elevators safe, it made vertical cities possible. Within a decade of that Crystal Palace demonstration, buildings started climbing. The first passenger safety elevator was installed in a department store in 1857. By the 1880s, the first skyscrapers were rising in Chicago. The home insurance building in Chicago, often called the first skyscraper, was 10 stories. It opened in 1885. By 1913, the Woolworth Building in New York reached 57 stories. The Empire State Building hit 102 stories in 1931. None of it without that spring and those jaws. Here's what's remarkable. The fundamental principle hasn't changed. Modern elevators use governors, electromagnetic systems, multiple redundant cables, but every single one still has a fail-safe brake that works on Otis's principle. Tension holds the brake back, loss of tension releases it. The failure is the trigger. And that philosophy, the idea of fail-safe design, spread far beyond elevators. Aircraft control systems that default to stable flight if hydraulics fail. Nuclear reactors where control rods drop automatically if power is lost. Emergency brakes on trains that activate when air pressure drops. They all use Otis's insight. Don't make safety something you activate, make danger something you actively suppress. And when that suppression fails, let physics do the work. Think about what that means for your life. Right now, there are roughly 18 million elevators operating worldwide. They make 18 billion trips per year. You probably rode one this week without thinking about it, maybe even today. That casual confidence, that complete absence of fear when you step into an elevator, exists because a 42-year-old bedframe mechanic looked at a broken wagon spring and thought, what if we're thinking about this backwards? Elisha Otis died in 1861, just 7 years after that demonstration. He never saw the skyscrapers his invention made possible. He never knew that his company, Otis Elevator, would become a global giant installing elevators in 200 countries. He just knew he'd solved a problem. He'd made a dangerous thing safe. The next time you step into an elevator and you press that button, you're trusting a principle invented by a guy who made bed frames for a living, a guy who understood something profound, that the safest machines aren't the ones that never fail, they're the ones designed to fail safely. And that insight, that reversed logic, it lifted the entire world.